Hello everyone, welcome to Stanford Geothermal Workshop 2021. I'm Ben Adams, I'm a professional mechanical engineer. I'm going to give my presentation today on analysis of the demonstration of a CO2-based thermosiphon at the SECARB Cranfield site, which is a CO2 sequestration site in Mississippi. This work is work that I performed as a postdoc at the University of Minnesota and also in collaboration with my co-authors, Mark Fleming, Jeff Belicki, Nagasri Garapati, and Martin Osar at The Ohio State, Milwaukee School of Engineering, West Virginia University, and ETH Zurich. In January 2015, a field test of subsurface CO2 recirculation showed no sustained circulation rate, which is opposite of what we expected. And this, a thermosiphon is a closed-loop, buoyancy-driven circulation of a geologic fluid with the surface occurring without pumping. So basically, in a CO2-based geothermal system where you have CO2 in the subsurface, because the density of the fluid changes so much, we expect there to be a buoyancy-driven effect where the fluid circulates itself. But that didn't happen at the field test in 2015. So in this analysis, we look at some hypotheses for why that might be. We find is the thermosiphon generated flow rate is a function of the wellbore densities, that accumulating water in the production well could drive the flow rate of the self-circulating thermosiphon flow rate to zero. And importantly, a self-sustained thermosiphon is not necessary for the successful deployment of CO2-based geothermal. So what is a CPG system, or a CO2-based geothermal system? There's a diagram here on the left. You have fluid at the surface. You pump down an injection well, high density cool CO2. It flows through the reservoir, extracting heat, getting warm. You produce the warm CO2 up the production well to the surface, run it to a surface plant where you expand it in a turbine to generate power, cool it down, and then re-inject it back into the deep reservoir. And we found that the power generated at moderate depths, permeabilities, and geothermal gradients is greater for a CO2-based geothermal system than a water geothermal system. In this diagram here from our 2015 paper, we show that a water geothermal system are the orange lines, and the CO2 geothermal system are the black lines. And just at 2.5 kilometers depth here, you can see that the CO2 system generates much more power than the water system. And that's basically due to the CO2 having a lower viscosity but a similar heat capacity to water. So the pressure losses within the reservoir are much lower than water, so you can just extract it easier. You can extract the geothermal heat easier using CO2. It has other advantages too, like the CO2 is compressible. So the density changes a lot with temperature, which creates this self-sustaining thermosiphon that we're talking about today. So you don't have to pump it, but usually if you pump it, you can increase the amount of power that it generates. So you have fewer pumping requirements. So for example, here in the plot above, the solid black line shows CO2 geothermal with pumping, and the dotted line shows the power generated if only the thermosiphon generated flow rate is used to circulate the fluid. So you get a little more electricity out if you also pump it, but you don't necessarily have to. So this is CO2-based geothermal, and it's usually built on top of a CO2 sequestration site to generate electricity with a stored CO2 to try and provide some return on the sequestration investment. So the CO2 circulation test in 2015 at the SECARB CO2 sequestration site didn't create a thermosiphon generated flow rate as was expected. So in the 2014 paper here on the left, we show the mass flow rate versus depth for a CO2 system and a water or brine geothermal system at three different geologic temperature gradients. So we show that basically for any depth greater than 500 or 700 meters, you get a non-zero thermosiphon generated flow rate that should happen immediately in the system. And the effect isn't isn't as strong for water because the density of water is more or less constant until you get it really hot. So you need to have these great depths and temperatures to get the water to have a thermosiphon generated flow rate as well. Now in the SECARB sequestration site, when they did a thermosiphon test to try and see if the CO2 would circulate itself, the flow rate tended towards zero. The flow rate being the green line here. They tried to circulate it 3 times with a venting period followed by a siphoning period. So in the venting, they would release some CO2 to try and get the flow to start circulating. And then they would close the system and see if the flow rate would be sustained. But unfortunately, it didn't. And in all the cases, the flow rate sort of asymptotically approached zero with enough time. So okay, that raises the question: what weren't we predicting, or where did we go wrong? And so we looked at the assumptions of the initial thermosiphon paper work that we did in 2014, and some key assumptions that we made in that paper were that there wasn't any heat loss within the well from the fluid to the surrounding rock, and also that we always had pure CO2 in the wellbore and never anything else like water. So we're looking at the effect of including these things on the thermosiphon in this analysis. The thermosiphon generated mass flow rate is a function of the injection and production well effective densities. So the system that we modeled here in this analysis is on the right. You have just some cooling and pumping at the surface, an injection well, and a reservoir with pressure losses. And then the fluid comes back up the production well. The Cranfield site had 129 C reservoir and 3.2 kilometers depth. And basically, an injection or production well is just an expansion or a compression process for the fluid, which is represented by this equation over here. So the integral of the change in pressure over density is equal to the change in enthalpy. And this enthalpy change is more or less fixed. It's just the change in potential, the change in height of the system. So basically, the resulting pressures between the entrance and the exit of a well is only determined by how the density of the fluid changes. And in the CO2 system, the density changes a lot. So if you solve for this, the pressure that's generated by the thermosiphon, which is just the difference across the bottom of the reservoir here, first at a first assumption, if you exclude wellbore heat losses, it's just the difference in effective density of the injection well and the production well times the depth times G. In a system, basically this is the pressure generated by the thermosiphon, and then the mass flow rate that's going to result is just where this pressure is consumed by the frictional losses of the reservoir, wells, and surface equipment. So what that means is that the mass flow rate that results is just proportional to the difference in densities between the injection and production wells. This is why for water, for instance, where the density is more or less constant, the resulting mass flow rate is about zero. But for CO2, when the injection well density is maybe twice as large as the production well density, you can generate a substantial mass flow rate here. So to kind of get an idea of how strong the thermosiphon is, or the mass flow rate that will result, we can look at the density profiles of the fluid within the wells. This plot here is for pure CO2, and it shows the density profile within the wells, this tulip plot. For depth, this is the surface, and this is 3.2 kilometers depth. The orange line in the middle represents the density profile at time 0, when the pressure and temperatures of the fluids are equal. And as time moves on, the injection well density increases as the influx of heat into the injection well gets smaller. It allows the fluid to be colder all the way down, and so the density on average increases. And the same thing for the production well. As time goes on, the loss of heat to the surroundings gets lower in the production well, and so the density the fluid stays hotter and the density stays lower. So you can see that just as time moves on, and this is a 20-hour window here, the difference between injection and production well densities grows, and so the thermosiphon resulting mass flow rate then will also increase. So you can see in the inset here on the right, we just show that the mass flow rate versus time increases sort of asymptotically towards a non-zero value, which is, what we expect and find all the time, that there's just sort of a steady non-zero flow rate that results. So the question is then, what happened in the Cranfield case? And the best we can figure is that there was a high density fluid got into the production well, water, high density fluid, and filled it up, increasing the density of the production well. So this figure here shows that the water influx for 3 different levels. The chi is 10%, so we allowed 10% of each wellbore element to be filled with water. So when 10% of the element would fill with water, then it would go up to the element above it, and it would move. The well would fill up all the way to the surface. And if we let 50%, the blue lines are 50% of the element, of the mass of the element can be water, and orange is 80% of the element can be water. And in each of these cases, the water coming in was 2% of the total mass flow rate into the well. So of course, if you allow more fluid, more water to collect in each element, it takes longer for the water level to come up to the surface here. If you look at the mass flow rate here, you see that the black line, where only 10% of each element is water, the mass flow rate more or less didn't change. It kind of just reached this asymptotically approached this non-zero value. But for the 50 and 80% values, there was a maximum flow rate reached, and then it started going down as the wellbore density increased and got very high. And basically only the 80% one, the orange line, would we expect it to go to zero in this simulation that we did. So that's just to show that you need almost the whole well to be water. The whole well needs to be filled with water to stop the thermosiphon generated flow in our simulations. This shows the tulip plots again for 50% water and 80% water. The density of the production well, the red line in this case, is the production well density. As it fills with water, the bulk density of the well gets very high. It gets to be larger than the injection well density, the black line, and then in that case you can stop the circulation of the fluid. You can stop the thermosiphon effect. It's important to remember, though, that the thermosiphon generated mass flow rate is not required for CO2-based geothermal to be successful. Ultimately, this is just it's just a geothermal system. It's just where you're trying to extract fluid from a reservoir and bring it up to the surface, bring hot fluid to the surface, and do something useful to it. In order to do that, you just have to pump it. In a water geothermal system, you pump to circulate the fluid between the surface and the reservoir, and the CO2 system is the same. You can just pump to circulate the fluid. So if you're having a problem where at the very start, you have a water influx into the well because the reservoir hasn't dried out yet, you can just pump to get whatever flow rate you need and let the reservoir dry out. Ultimately, the CO2 system just has lower friction losses in the reservoir, so it's just easier to extract the heat. So, the thermosiphon is a nice benefit, but, isn't necessary to do CO2-based geothermal. And like I showed before, ultimately, you can make more electricity if you pump it anyway. Even if you do have a non-zero thermosiphon flow rate, you can still pump it to get more electricity. So it's likely any system you make will have a pump no matter what. So the water accumulation in the system isn't necessarily a deal breaker. So the thermosiphon generator mass flow rate is a function of just the wellbore density, the difference in the injection and production well densities. Accumulating water in the production well was what had the ability to stop the circulation rate. And importantly, the self-sustaining thermosiphon is not necessary for the successful deployment of a CO2-based geothermal system. Thanks for listening, and have a look at our paper in the 2021 Stanford Geothermal Workshop Proceedings.